Hong from National Technical University. He will also tell us about gravitational lensing. Let's welcome Simon.
Thank you, Thomas. So I'm Simon Ho, a first-year PhD student from ANU, and I did my master in NDHU with Kajiya-san and Tomo-san. So today I want to present our work about the future constraints of dark matter with gravitational lens FRBs detected by BURSTT. And this work is submitted to APJ recently, and in collaboration with the following authors. So first, I want to outline my talk. I will talk about the background information of FRBs just briefly, and then I will talk about the challenges faced in FRB observation, and finally I will talk about the estimation and constraints. So first, the background. Fast radio bursts, also known as FRBs, they are in millisecond duration but Jansky level brightness. This opens us a new parameter space that we have never studied before. So since 2019, there are more than 20 Nature or Science papers that have been published, but so far we have no consensus about the origins of FRB. And more FRBs are detected over years. So one of the interesting and unique points of FRB is that they can be used as a cosmic probe. Like in Munoz et al. 2016, they proposed the idea of using FRBs to constrain dark matter. And Hashimoto et al. 2019A, they proposed the idea of using FRB to constrain dark energy. Today I won't talk about dark energy, but only dark matter. So how to constrain dark matter? We need to find one thing which is called the gravitational lens FRB. And later I will just call it lens FRB. So we all know that what a lens galaxy is. So from the left image, you can see that a lens galaxy is lensed by galaxy cluster. So the light from the galaxy is banded by the G field of the galaxy cluster. So from the telescope image, you can see the image of the galaxy is banded, something like this. For FRB is similar, but not exactly the same. Like what the previous speaker Dylan has mentioned, there is a double screen model in the FRB model, which is proposed by Learn et al. 2022. So FRB signal will be lensed by this double screen model, and finally you will see separated images by a time delay of tau lens from the telescope image. So how exactly lens FRB can help us constrain dark matter? I will tell you a story about this. So one of the most interesting thing that you study in Australia is that you can see some creatures you have never seen before, like kangaroos. So this is an image that I took in the Mount Stromlo, which is my institute located at. So you can see there are so many kangaroos up there. And sometimes you can see there are something. Sorry, it's a bit leaky. So you can see something on the ground which is shown by the right image. So these are not blueberries, but actually kangaroo poops. So you can imagine that those kangaroos are invisible like dark matter. So one of the methods to calculate how many kangaroos are up there on the mountain is to find how many poops are on the ground. So you can roughly calculate how many kangaroos are on the mountain. This is similar to how you constrain dark matter with gravitational lens. You just how many detection of gravitational lens FRB, then you can constrain the rough number of dark matter fraction. So in the past, there are other constraints of dark matter, like previous microlensing surveys. They probe the mass ranges of 10 to the minus 7 to 10 solar mass. And CMB, they constrain the mass ranges of over 100 solar mass. And in Munoz et al., they proposed a new idea of probing dark matter with millisecond FRBs in the mass range of 10 to 100 solar mass. And the form of dark matter which is called primordial black holes. This is a very popular candidate of the hypothetical origin of dark matter. So far we don't have information of this window, which is 10 to the 100 solar mass, and because we haven't found primordial black holes yet. And actually, FRBs can help us with this. So next I will talk about challenges. So we need to find lens FRB rights, but we haven't found one yet. The most successful survey in finding FRBs has been CHIME. So before CHIME, there were only like 100 FRBs. But after CHIME, thanks to CHIME, we have more than 600 FRBs nowadays. But none of them are lens FRB, which is quite a pity. So there are mainly two challenges faced by FRB observation. The first one will be the lack of localization capability. So we don't have the location of FRB, we don't know the ratio of them. The second one is we don't have enough field of view for the observation. So we want a large amount of FRB detections, but now only like 600 of them is not enough to even find a lens FRB. So today I wanted to talk about BURST, which BURST can actually help with finding lens FRB in the future. So in the first phase that we have talked in the previous 2 days is referring to the BURST 256, which the number refers to the number of antennas of BURST. And later, in the future, because of the modular nature of BURST, we are trying to expand BURST 256 into BURST 2048, which we have 2048 number of antennas. This is like an evolution in Pokemon, so you can see that the sensitivity of BURST is highly improved. So I would say BURST 2048 can help finding lens FRBs in the future. And later I will talk about the estimation. So our estimation is actually based on a paper which is Menes et al. 2016. So in their paper, they calculate the lensing probability by that equation you can see here. And first they assume the fraction of dark matter, which is equals to 1, and cold dark matter density, which is equals to 0.24. And later they assume there are like 10,000 FRBs we can detect. And then if there's no events out of them, for 10-year observation, and then they can constrain dark matter, in this case, from 10 to about 100 solar mass by using 0.3 millisecond and 3 millisecond lens FRBs. In our case, we first calculate the number of FRBs expected to be detected by BURST 2048. So using this equation here, we can calculate the FRB event rate, which is proportional to the field of view divided by the system equivalent bus density to the power of 1.5. So we have some parameters of CHIME and BURST, so we just simply scale it. Like in this case, BURST 2048 is 25 times better than CHIME in the field of view, but like 6 times worse in the sensitivity. So we can roughly calculate, we can detect like 1700 of FRBs by 2048 BURST. And later we need to calculate the detection threshold of BURST 2048. So from this equation of James et al. 2019, we can see that if we input the number of the sigma threshold, the SEFD and time resolution, bandwidth, etc., we can get a number of about 12 Jansky millisecond for BURST detection threshold. And later we plot this, which is the fluence distribution of BURST of CHIME catalog in the CHIME collaboration 2021. So in this catalog, they have about 563 sources. And Hashimoto et al. 2022, they invert the redshift for those sources by using a DM contribution. And later we plot the fluence threshold for the detection threshold for BURST 2048 in this plot. So for those sources which is over this threshold are the sources we can detect by BURST 2048, which are about 100 sources. And we also plot the redshift distribution here. So the orange one is the one for BURST 2048, and this is actually the NZ in the lensing probability equation, you can see. So this is our estimation of the number of lens FRB we can detect in the future. So in total, we have like 1700 of FRB's detection. And for lens FRB, we have about 26 of them. And how to get this plot is that we sum up all the optical depth of each FRBs in the 500 sources.
2 minutes left.
Yeah, in each redshift beams. And then we can get this plot. And we assume the lensing mass we have is 0.001 solar mass and in nanosecond FRBs. So the lensing fraction from this work is about 1.5%. This may be a little bit higher than the Munoz et al. 2016 because we are considering the best time resolution we can get. So if we consider the same parameter we are using in this work with Munoz et al., we can get a lensing fraction which is 0.2%. So now it is in the same order as Munoz et al. And later if we set the fraction of dark matter as free parameter, we can get this dark matter constraint by BURSTT 2048. So above you can see other constraints by other surveys. Below you can see this rainbow here, which is the BURSTT 2048. So from nanosecond FRBs to millisecond FRBs, those are the constraints of BURSTT 2048. So we can probe down to about 10 to the minus 4 in the lensing mass and about 100 for the millisecond FRBs, which cover the window we have never seen before. And also we have some maybe better constraint in the lower region. So our summary is here. So we can predict a number of about 1,700 FRBs per year for BURSTT 2048. And out of them, we can detect 26 lens FRBs from them. So with BURSTT ability to detect nanosecond FRB, we can kind of constrain primordial black holes to the form of dark matter in the range of 10 to the minus 4 to 100 solar mass. So BURSTT can help us with the lensing FRB observation in the future. Thank you.
Okay, questions, comments, please? Any from online? No? Okay, here, you have a question?
Hello, Simon. Thanks for your interesting talk. And I'm curious about what is the advantage of BURSTT compared to other radio telescope to research the dark matter?
Oh, that's a good question. So we know that the field of view of BURSTT is really large, like 1 stereo. So this is one of the largest surveys in searching FRBs. So to search a lens FRB, we need to have a large enough number of FRB detection. So that's the advantage in this, I think.
Online question?
Yes. Sorry, Carleton University.
Yeah, hi, Martin Sands here. I have a question about the third dot point there. So it says the lensing mass 0.01 solar masses and the timescale of 1 nanosecond. Was that timescale the resolution of your instrument or the expected delay between lensed images?
You mean the nanosecond one?
Yeah.
Yeah, that's the best resolution that BURSTT can achieve in the future because we can use the buffer voltage to record it.
Yeah, okay. Thank you.
Thank you.
Okay, any other questions, comments? Okay, if not, time is up, so let's thank Simon again.